One way that you can tell how physically fit a person is by checking their resting pulse rate. And so in this problem, we're going to look at 10 people who volunteered to test an exercise device to see if the device would lower their resting pulse rate. So they used it 3 times a week for 20 minutes each time. They had their pulse rates, resting pulse rates, measured before they started using the machine and after they started using the machine. And the results are here. They checked 6 weeks after they started using them. So they used them 3 times a week, 20 minutes each time for 6 weeks. And we've got the before and after of their pulse rates here. And we want to know, does this exercise machine work? It claims that it can make you more physically fit, and we're going to check that by checking resting pulse rates. And we just want to know, is there any evidence that the device works? Now, you hopefully can see right away that we would need to do a t-test in order to perform this calculation. The problem with doing a t-test here is that we don't meet all of the conditions that we would normally need to meet in order to do a t-test. We don't meet the random condition. That's not that big of a deal if we assume that our volunteers were a representative sample. In other words, we didn't go to get exceptionally out of shape or exceptionally in shape people. If we assume these are a representative sample of all men, then that's fine. However, we do have one major problem, which is that these are not independent. Alan's pulse rate before he starts using the machine and Alan's pulse rate after he starts using the machine, those numbers are not independent because they're both Alan. Alan is the person that we're measuring both times, and I'm sorry to say, Alan's pulse rate is not independent of Alan's pulse rate. So we violate one of the conditions that we have to have in order to do a standard t-test, and that is the independence condition, and there's really no way around it. You can't assume they're independent because we can't assume that Alan is independent from Alan. So we need a new method in order to perform a t-test. And we're going to get a little tricky here with how we're going to get around the fact that we do not meet the independence condition. And the way that we're going to get around it is that although Alan's before and after pulse rates are not independent of one another, what is independent is the difference between each one of these guys' pulse rates before and after. In other words, if I want to see, did Alan really improve? Did his heart rate really go down? I could do his after, subtract his before, and of course in Alan's case, 73 minus 73 is 0. So his average difference was 0. Then let's look at Brandon. Brandon had 83 before and 79 after, which means he lost 4 beats per minute. His heart rate went down 4 beats per minute. 79 minus 83 is -4. And so on. I can go all the way down. Carlos went down 4 beats. David went down 1 beat. Edwin went down 4 beats. Franco went down 8 beats. Graham went down 3. Hans went down 2. Ivan went up 1. And Jorge went down 3 as well. Now these differences in their pulse rates, those are independent. Alan's improvement is independent from Brandon's improvement, which is independent from Carlos' improvement, and so on. So when you see these 2 columns, you might be tempted to say, oh, it's a 2-sample t-test. But we can't do a 2-sample t-test because these columns are not independent of one another. What we can do is a 1-sample t-test, but using the differences instead of using the 2 columns on their own. So what I'm going to do is put in these differences into my calculator. So the reason that I'm putting them in the calculator is for a couple of reasons. Primarily it's because I want the calculator to find the average and the standard deviation for me in a minute. But also I'm putting them in because I need to be able to do a quick graph of these to make sure they meet the nearly normal condition. I know they don't meet the independence condition. I'm going to assume that they meet the representative sample condition or random condition. The problem says they volunteered, but I'm going to assume they're a representative sample. That's a fair thing to assume. But I do need to make sure that I meet the nearly normal condition. So I've got these 10 numbers, the differences put in here. So I'm going to use my calculator here to do a quick graph. That's a dot plot. Dot plots are fine, but I prefer histograms. So there's a histogram. It's not perfectly normal, but it doesn't have to be perfectly normal. It needs to be nearly normal. And so the first thing I'm going to start off by saying is I'm going to do a quick sketch here. Let's start on a clean sheet of paper. I'm going to do a very quick sketch of what I see. Now you might see something different on yours depending on your window and the version of the calculator you use, but I'm going to say the data is approximately unimodal and symmetric. And I'm going to assume that these guys are a representative sample. In other words, I didn't go to the gym and get a whole fleet of bodybuilders, or I didn't go to the local buffet and get a whole bunch of morbidly obese people. I'm going to assume they're representative. Okay, so now that I've got that done, I'm going to go ahead and write my hypotheses. And here's what the hypotheses are going to look like. I got my null and I got my alternative, and I'm doing essentially a one sample t-test. But what I'm checking is the difference between the two, or more specifically, the average difference between the two. And so my null hypothesis is that the average difference, there's my symbol for average, I'm going to put a D there, so difference. The average difference, I think, according to the null hypothesis, is going to be 0. I think there will be no difference. The alternative hypothesis will be that the device did work, which means the difference should be negative. If you go back and look at my numbers, see if they improved. If the device worked, their heart rate went down, and I got a negative number, -8, because their heart rate went down. So my alternative hypothesis is that the average difference is going to be less than 0, or the average difference is going to be negative. Okay, so those are the two hypotheses that I'm going to check. I made sure the data was approximately unimodal and symmetric, and I'm assuming that these 10 guys that volunteered are representative of all guys. So what I'm ready to do now is a t-test, and this is going to look exactly like every other kind of t-test you do. I'm going to have 10 total things, and that means 9 degrees of freedom. I'm going to have to figure out what the average difference is here in a minute. I'm going to write that as D bar. I'll figure that out in a minute. And then I want the standard deviation of the difference. I'll figure that out right now. Let's go back to the calculator. I'm going to close the quick graph just so I've got a little more space. And here's my difference column. And when I go to my statistics menu, I'm going to do stat calculations. I'm going to do one variable statistics. And the list I'm going to use is this diff list. I'm going to go ahead and put the results in column B. And here's everything that I need to know. The average is -2.8. And if I go down a little ways, the standard deviation I'm going to use is 2.53. So, average difference, -2.8. Standard deviation, 2.53. Alright, so these are all the mechanics that I need. Now I'm going to go ahead and set up the test. So T equals what the difference actually was, -2.8, minus what I thought the difference should be. Remember, my null hypothesis was 0. The difference should be 0. Over the standard deviation. And the standard deviation is real simple. The average standard deviation was 2.53. And I'm going to do over the square root of n, in this case 10, just the regular formula for the standard deviation. So what I want you to notice is that this formula here for the t value looks identical to our one sample t-test. It is identical in every way. The only change is right here, this number I got by finding the differences between the two groups. So I'm going to stop right here with doing the calculations by hand. I'm going to have the calculator do the rest for me. I'm going to go back to my calculator, and this time I'm going to do a t-test with the difference column. So I go Menu, Statistics, and Stat Tests, and I'm going to just do a t-test. It's a one sample t-test. So let's select that. I'm going to use data because I have a list of data in the calculator. And that list is the diff column. Let's put in my null hypothesis, which was 0. My null hypothesis was there will be no difference. The list is the diff, that's what I named it. My alternative hypothesis, I did as less than. I believe the difference is going to be less than 0, so I need to change this, that the average is going to be less than my null hypothesis. I don't want to put the results in column B because I already have the 1var stats in column B and C, so I'm going to change this to column D so I can keep those 1var stats handy just in case. And then I'll go to OK. And there's my set of data. My t was -3.5, and my p-value is 0.003362. And of course, there's my degrees of freedom, and there's my average that 1var stats already told me. So the calculator says that this equals -3.5. which means my p-value is 0.003362, or if you like percentages, you could write that as 0.3362%. I wrote all of the decimals. You don't really need to. I could have rounded that to 0.34%, and that would have been totally fine. So I would say by any standard that is a low p-value. It's less than half of 1%. So I'm going to go ahead and write my conclusion now. That p-value is low, so because the p-value is low, I reject the null hypothesis. The null hypothesis was that the device didn't work. Remember my null hypothesis, there is no difference. The difference between the two is 0 before and after. I rejected that null hypothesis. I think there is a difference, and my alternative that I tested was that the difference was negative, meaning the device works. So I'm going to say I have strong evidence the exercise equipment, or the exercise program, is effective at reducing resting heart rate. Now this is identical to a one-sample t-test in every way, except this is a t-test that you do when you have two sets of data that are not independent. When your data is not independent, you do this type of t-test. Functionally, it is identical to a one-sample t-test, but we have a special name for it. It's called a matched pairs t-test. And matched pairs is sort of a fancy way of saying do a one-sample t-test, but it's called matched pairs if the results are not independent. And the only difference between this and any other t-test is that when I had my two rows of data, rather than putting these two rows into the calculator, I found the difference and put the difference into the calculator, because although the before and after were not independent of each other, these differences are independent of each other. And that's sort of a tricky way we can use to get around the fact that we did not meet the independence condition in this problem.